We're going to begin the spring semester of Pre-AP Chemistry by combining chapters 8 and 9 into a single unit. The reason that we do this is these two chapters serve as our introduction to a portion of chemistry known as stoichiometry. Stoichiometry deals with the quantitative relationships associated with chemistry. Quantitative from quantity, therefore involving numbers and mathematical calculations. So stoichiometry is all about the numerical relationships in chemistry. There are two distinct categories of stoichiometry. The first category is known as composition stoichiometry, and this is actually what Chapter 8 is devoted to. In fact, Chapter 8 is entitled Chemical Composition. But composition stoichiometry deals with the quantitative relationships, the numerical relationships among the elements in individual compounds. Examples of composition stoichiometric calculations would include a percent composition calculation, an empirical formula calculation, or a molecular formula calculation. And again, composition stoichiometry deals specifically with the relationship of the elements in individual compounds, and that's where we'll begin in Chapter 8. The second type of stoichiometry is what is known as reaction stoichiometry, and that's what Chapter 9 is devoted to. Reaction stoichiometry talks about the relationships between reactants and products in a chemical equation. In the first example that I've listed here, calcium carbonate decomposing to form calcium oxide and carbon dioxide gas, a typical reaction stoichiometry problem might be I tell you exactly how many grams of calcium carbonate you've got, and then I ask you, when the decomposition reaction is complete, how many grams of calcium oxide would I then have? By the same token, I could tell you that I want to acquire or end with a certain amount in grams of calcium oxide. So I could turn around and reverse the question, okay? If I want this many grams of calcium oxide, how much calcium carbonate would I need to begin my reaction with? So what I want you to be aware of is these types of calculations can begin with a reactant where you're asked for a product, or you can be told you need to have so much product, how much reactant would you need? In the second scenario, the reaction between zinc and hydrochloric acid, just so you're aware of this, I might say, okay, I'm going to begin with a certain mass in grams of zinc metal, and I'd like to be able to determine what the volume in liters of hydrogen gas would be if I used so many grams of zinc. Again, I can reverse the scenario. If I wish to produce a certain quantity of hydrogen gas, I can turn around and ask how many grams of zinc would be necessary to accomplish that. So in reaction stoichiometric calculations, I can begin with a reactant and ask a question about a product, or I can begin with a product and ask for the amount of reactant that would be necessary to obtain that amount of product. There are 5 basic types of reaction stoichiometric calculations that we'll be looking at in Chapter 9. You'll see them listed here: mass-mass calculations, mass-volume calculations, volume-volume calculations, limiting reactant calculations, and percent yield calculations. And again, these are reaction stoichiometric calculations, and they're what we'll study in Chapter 9. In order for us to be able to make stoichiometric calculations of any type, whether they be composition stoichiometric calculations or reaction stoichiometric calculations, we have to be able to use our periodic tables properly and obtain certain information from those periodic tables. So what we want to do now, before we even begin Chapter 8 and our study of chemical composition, is review some basic terminology going back to Chapter 4 and our study of atomic theory. And it's all ultimately about the periodic table. Remember, if you will, that the periodic table is arranged according to atomic number. Atomic number is simply the number of protons that make up the nucleus of an atom. If you want to identify the type of atom that you're looking at, you would count the number of protons. And for example here, what we've got is the atomic number of hydrogen is 1, that of gold is 79. On the Montana Tech periodic tables, the atomic number is always listed in the upper right-hand corner for each element. The second term is what is known as average atomic mass, and it appears in the upper left-hand corner of each element's block on the periodic table. And it's really not important right now that we be able to define this term. Okay? That's not what's important. Right now, the most significant thing about average atomic mass is that you understand it is found in the upper left-hand corner of each element's block on the periodic table. The one thing I might add here, in the case of hydrogen, where we see its average atomic mass is 1.00794, is that that is actually expressed in a unit known as the atomic mass unit. So technically, the average atomic mass of hydrogen is 1.00794 atomic mass units, or we abbreviate that AMUs. And it is not uncommon for different periodic tables to list slightly different average atomic masses for an element. What is so important about this average atomic mass here is the next term, and that is mass number. And this is probably, for stoichiometric purposes, the most important number that we'll need to be using from our periodic table. Mass number technically is defined as the sum of protons and neutrons that make up the nucleus of an atom. Again, it's not the definition here that's important, it's what we do with this number. Okay? Going back to the example of hydrogen, where its average atomic mass is 1.00794 AMUs. That's its average atomic mass. Its mass number, if I take this number here and round it off to the nearest whole number, I'm going to have the most likely mass number for hydrogen. And in this case, it would be 1 AMU. Going down to lithium, its average atomic mass is 6.941 AMUs. If I round that off to 7, that's going to be the most likely mass number for lithium. And the truth is that when we make stoichiometric calculations involving hydrogen, we're going to use as its mass or mass number 1. For lithium, it's going to be 7. For magnesium, 24.3050, we're going to round that to 24. That's close enough for our purposes. Sodium, 22.989768 AMUs. We're going to round it to 23 AMUs. And this procedure of rounding to the nearest whole number works for just about every element, with a couple of exceptions that we will routinely encounter. And the two most common exceptions that we'll routinely encounter are for that of copper and chlorine. Copper is listed at 63.546 AMUs. The question would be, do I round that up or down? And the truth is, for calculation purposes in this class, we're going to maintain a mass for copper of 63.5 AMUs. For chlorine, 35.4527 AMUs. we're simply going to round that to 35.5 AMUs. And so those are two of the more common exceptions that we'll encounter when it comes to this rounding process. So at this juncture, what you need to be able to do is identify or locate an element on the periodic table based on atomic number, and you need to be able to locate for that element its average atomic mass, and from that number be able to convert that to a mass number so that you can use it in stoichiometric calculations. And this will bring to an end or conclude our quick review of the periodic table and our introduction to Chapter 8 in chemical composition.